Hello and welcome to another session of the review materials for Calculus 3208 presented by CDLI. Today we're looking at our second topic in limits in continuity, which is limits from graphs and one-sided limits. So some of the stuff that we would have started in our last session, but we're going to get into some more detail here. Okay, so let's look at, first of all, the key concepts that we're going to focus on in this session. First one is we're going to talk about limits from the left and right for a function graphically, and then we're going to, based on what we come up with there, refine our definition of a limit of a function. Okay, so we're going to tweak the definition that we saw in our last session, or that you would have based on a conceptual understanding of limits from last day, and we're going to take it to the next level. All right, so we're just going to start by talking about one-sided limits. And the first thing you need to know about one-sided limits is that we have a special notation to represent them. So if you look at what we have in some of the questions that are written over here, you'll notice that it looks like there we've got the limit as x approaches 2, and it almost looks like with an exponent of a negative sign. But what that means is if I have a limit as x approaches a value, let's call it a, and I put a little negative sign there, of f of x. Or if I have a limit as x approaches a number a, and I put a little positive sign up there, where an exponent would go, of f of x, then that means we're talking about the limit of the function as the values of x approach the given number a, but only from one side. So for the first one up here, we're only talking about what happens as x approaches a from the left. And in the second one, we're only talking about what happens as x approaches a from the right. And so let's take a look at our graph and see if we can figure out in the context of this problem what that really boils down to. So on this particular graph, we're asked to find the limit as x approaches 2 from the left. We're asked to find the limit as x approaches 2 from the right, and that one didn't come out very clearly, so I'm just going to make sure that that looks like a plus sign there. So that should say plus right there, and that's probably no clearer, but anyway. And then it says we have to find out overall, what's the limit as x approaches 2? And then we have to evaluate the function f when x equals 2. Okay, so a bit of strange business going on here. Why are they not all the same thing, and why are they different? So let's see. So the first one says we have to evaluate the limit as x approaches 2 from the right. So on our graph, what we do is we follow our curve from values that are, as x approaches 2 from the left. Excuse me, I got to watch my language here. So the limit as x approaches 2 from the left, I'm following my curve toward where x equals 2, and I'm only allowed to come from the left-hand side. And if I do that, and I come from the left, I'm going to end up really close to this point down here that has a hole in it, which we don't have to count though, because remember, a limit is a boundary. We don't actually have to get to that point. So what are the y values approaching as x approaches 2 from the left? Well, the closer this curve gets to that point, the closer the values of y are getting to the number 2. So for the first one, we can say that the limit from the left here will be equal to 2. Then we have to tackle the limit from the right. So we're going to look now at what happens, the limit as x approaches 2 from the right. So I'm going to follow this all the way along from the right-hand side, and I'm getting really very close to this point that I'm not allowed to touch, but I can get infinitely close to it. So when I do that, I notice that as x gets closer to 2, as I move along here, my x values are getting closer to 2. And as I do that, as I move up, my y values are approaching 3 as I get there. So what happens here is we say that the limit as x approaches 2 from the right is going to be equal to 3. All right. And the third one we have to evaluate is what's the limit as x approaches 2? Without reference to left or right at all, what's just the limit as x approaches 2 of this function? Well, the rule is if the limits from the left and the right are not the same answer, then we don't have an answer for that. What we say is that the limit does not exist. So here, the limit does not exist. Sometimes you'll see textbooks or even teachers or professors or someone might write DNE or LDNE for limit does not exist. Sometimes you'll see that. But to be quite perfect about it, we should write out the words does not exist. Okay, the last thing we have to do in this example is we have to evaluate what's f of 2. Well, f of 2 has nothing to do with limits. We just want to know what's the value of this function, or what's the y-coordinate for this function when x equals 2. So on my graph, I'm just going to go to where I have a point that has an x-coordinate of 2. And when I have an x-coordinate of 2 here, I see that my y-coordinate is 4. Okay? So we have 4 different questions that are asked that all look very similar, but we have 4 different answers for those. Okay, let's take a look at another situation now. Or sorry, we're going to, based on what we just learned, we're going to define the basic limit theorem about when limits exist and when they don't. So, what it says here is that the limit of f of x as x approaches a is equal to L, so it has some numerical value L, if and only if our left-hand limit and our right-hand limit, or our limits from the left and the right, are equal to each other. So if those two are equal to each other, then we are in fact having a limit that is equal to L right there. Okay? So we have to have that. And also it says to note that the value of the function f of a, so wherever the dot is for the function at that point, has no bearing. So it doesn't matter where that is. It has nothing to do with the limit. So in terms of just evaluating the limit, we don't care where the function actually is. We just care what it approaches as we come from both sides. All right. So let's move on here, and we'll jump on to an example. And it says, evaluate each of the given expressions using the graph shown. So the first one says we have to evaluate the limit as x approaches -1 from the left. So I'm going to follow this curve from the left side toward the point where x equals -1. And as x approaches -1 along that curve, the y values are getting close to +1. So that's pretty straightforward for us. We'll just fill that in. This limit right here is going to be equal to +1. Now we're going to try the limit as x approaches -1 from the right. So to try that one, we follow the curve from the right-hand side, and as we get there, we get closer and closer, and there's not supposed to be a gap in the function here. That's just where the coordinate was written on the axis there. But this is a nice smooth curve. We follow it closer and closer and closer, and as we get really close there, it looks like the y-coordinates are approaching something in between -1 and -2. I'm going to venture a guess there that that's at about -1.5. So let's fill that in. We're going to say that our limit from the right is about -1.5. Then we want to evaluate the limit overall as x approaches -1. So since our left and right hand limits don't agree, this one does not exist. So there's no limit there. It does not exist. Okay, and the last thing we have to figure out is what is the value of the function f at x equals -1, and for that we don't want this guy up here where it's the hollow circle. We want the dot that's filled in like this one down here. So the correct answer here is f of -1 equals -1.5. Okay, so we have a value for that one. Next, example 2, evaluate each of the given expressions using the graph shown. Okay, so in this case, we have what looks kind of like a sinusoidal function, and it approaches a spot on the graph where there's a hole in it, and then from the other side we go off on what looks like a linear function that continues off, and we don't actually include the point there, but we remove it, and we're going to put up a point up on the top there instead. Okay, so first thing we're going to look at is what's the limit as x approaches -2 from the left. Sorry, +2 from the left. So on our graph, approaching +2 from the left here, we're going to follow along from the left side, get close to +2, and y is approaching 1. So our first limit here is going to have a value of 1. The second one, we're going to approach +2 from the right. So following our curve from the right there, coming down this way, we get close to +2, and it looks like y is also approaching 1. So in this case, we've got a value of 1. So it asks us what's the limit overall as x approaches 2. Wait a minute, there's a hole in the graph over here. Does that mean we can't have a limit? Absolutely not. As long as we're coming from the left and the right and approaching the same value, that limit does indeed exist, and it's equal to 1. Now we have to evaluate the function f of 2. So what is the value of f of x or y when x equals 2? And we can see right here that at where we've already drawn this arrow in right here, when x equals 2, the function has a value of 2. So those two things are not equal. Our limit is 1 and our function value is 2, but we're allowed to have that. Limits just have to approach the value. The function is where are you when you're actually at that point. Let's look at the next one, which says the limit as x approaches 4 from the left. So if I'm approaching 4 from the left here, then I'm coming this way towards 4, and it looks like our y-coordinate is approaching 2. And if I come from the right, same idea, our y-coordinate is also approaching 2. So for both of those first two questions in the next column, we're going to be approaching 2 from both of them. And as long as the left and right limits are the same, the overall limit is actually 2. And in this case, there's no hole in the graph at all. There's nothing removed and replaced or whatever. So right there we do have a point. So f of 4 is actually equal to 2. So the idea is that the limit exists whether the point is there or not. And the other idea that we have to worry about is sometimes we can see that we have a point in the same place and it's equal to the limit. Sometimes we have a point that's in a different place that isn't equal to the limit, and that is a significant difference, but it's not something that determines the value of the limit. We'll worry about that a little more in one of our further sections when we talk about something called continuity. Okay, so let's do some test or exam type questions here. This one's very similar to what we've just been doing, which is evaluate each of the given limits. If the limit does not exist, explain why. Everybody loves those explain questions on math tests, don't they? Okay, so let's look at the first one. The limit as x approaches -1. So as x approaches -1, we're going to come from the left and the right. So coming from the left, it looks like the limit as we approach x equals -1 is going to be at -2. And coming from the right, it looks like the limit as x approaches -1 is going to be at +1. So that tells us that this limit over here, we've got a disagreement between the left and the right. Sounds like politics. So since we have a disagreement between the left and the right, the limit does not exist. So this does not exist. And the reason is, and they ask us to explain, but we don't need to give a very detailed explanation here. All we have to say is it's because the limit as x approaches -1 from the left of f of x is not equal to the limit as x approaches -1 from the right of f of x. And that's a good reason to say why they're not the same, right from the definition. The next thing we have to do is evaluate the limit as x approaches 1 for our function. So we find our x coordinate of 1. We're going to get close to that from both sides on our curve, and from whichever side we come from, it's approaching 5. So that one looks like we're A-OK for our y value at that limit. It's going to be 5. And as x approaches 3, we'll follow the curve again. So coming from the right, we're going to get close to a y coordinate of 1. And coming from the left, we get close to a y coordinate of 1. We're not actually equal to 1 at that point. We're way up here, but that's irrelevant. The limit doesn't care where the function is. It only cares what it approaches. So in here, we can see that our actual limit in that case is going to be equal to 1. Okay, next question. This one says, consider the functions f of x, which is an absolute value function, and it's been translated in 2 different directions, and g of x, which is kind of a funny looking thing, which is an absolute value function divided by a linear function that's identical to what's inside the absolute value bars. So the first one says we have to find the limit as x approaches 2 of f of x. So right here. So sometimes when you get these funny functions like this, sometimes we call those special limits. So this is not really something that we're going to evaluate algebraically or whatever. It's a good way to go with a graph. So let's just draw a quick sketch of a graph for the first function. So I'm going to just rough out some axes here to start with. So there's a good vertical axis and a good horizontal axis. And we know what the graph of the absolute value function looks like. The graph of the absolute value function would be, it looks kind of like a V that starts off down at the origin like that, And in this case, we've got to take that graph and we're going to translate it 2 units to the right based on that, and 1 unit upward. So essentially what we have to do here is take that graph, move 2 units to the right and 1 unit up, and I'll move both components of the graph. So we end up over there. So we have an absolute value function that looks like this, and we do have an included point right here, and that point is going to have coordinates of 2 and 1 because of our translations. And of course, that absolute value graph would be allowed to continue in both directions. And it says we want to figure out what's the value of the limit as x approaches 2 of f of x. So if I come from the left and the right here, we can see that we're approaching the same value. So coming from the left towards 2 or from the right towards 2, both of our sides of our graph are approaching a y-coordinate of 1. So our first limit here is just equal to 1. That one's pretty straightforward. Now, this next function, the limit as x approaches 2 of this really kooky looking g of x that we've got over here. Okay, so let's try to draw a graph for that one. Well, it's not the kind of function that we can graph by using transformations or anything real simple, but there is kind of a neat way that we can think about this one. What we're going to say about this is we'll look at a quick table of values, x and y. And if I choose values for x that are negative numbers, or if I choose values of x, oops, let's make that a positive 1 right there, get rid of that. If I choose values of x that are positive numbers, let's see what happens to the values of y. So when x equals -2, over here, I'm going to get -2 minus 2, so the absolute value of that is positive 4 divided by -4, which gives us -1. When x equals -1, I get positive 3 over -3, which is -1 again. And at 0, we're just going to be equal to 0. Now, when x equals positive 1, like we have down here, when I fill that in, I get -1 on the top, and I take the absolute value of that, and when I get the absolute value of that, I get positive 1. Positive 1 divided by -1 is going to be a -1 down there as well. Oh, and look, yeah, I've made a mistake here. I'm going to go back and fix it. I forgot. At 0, when I fill it in, I actually get positive 2 over -2, don't I? So this one should actually be a -1 as well. Hope you're paying attention and you caught that before I did. All right. So then at 2, let's see what happens. If I fill 2 in, this is where I get 0 over 0. So I get a value of 0. So there's the first value we got for this function that wasn't a -1. Well, I wonder if we keep going, what's going to happen here? So let's take 3 and fill that in. If I fill 3 in, I get positive 1 over positive 1. And that's a value of positive 1. If I fill 4 in, I get 2 over 2, which is a value of 1. And if I fill 5 in, I get 3 over 3, which is a value of 1. So to give you a quick sort of rundown of what happens with this function, if we think about its graph, what's really happening is for all the values of x that are less than 2, so everything that's less than 2 out here, we get -1. So we'll put a 2 on here. And everything that's less than 2, we get a y-coordinate of -1. And for everything that's greater than 2, we're getting a y-coordinate of 1. And at the point where x equals 2, we're getting a y-coordinate of 0 right there. So when we're less than 2, we have a -1. So let's draw a line out this way. And then we'll draw a line when we're greater than 2, we get positive 1 out this way. And then we have to decide where to fill in circles, color them in, or leave them empty, or all that kind of stuff. So on this graph now, we know that at these points, we don't actually get to the 2, because when we're at 2, we're equal to 0. So this should be a colored in dot. So that graph looks kind of like this. So what does that mean in terms of our limit now? So let's figure this out. The limit as x approaches 2 from the left is going to be -1. And as we approach 2 from the right, it'll be positive 1. Uh-oh. So we put all that together, and what we figured out, after all that schmozzle, that this limit does not exist. Okay, so let's move along. So our next question says, for the function given by f of x equals this stuff, evaluate each of the following limits, and if they do not exist, explain why. Okay, so the first one, we've got a piecewise defined function here, and we're going to have to break it apart at x equals 0 and at x equals 1. So let's make a quick sketch of that one. So for our piecewise defined function, we're going to have intervals that change things up at 0 and then at 1. So let's put 1 here. So I'm not going to go into a lot of great detail about this. I'm just going to find out roughly what's this thing going to look like. So until we get up to 0, we're going to follow this first curve. And that first curve says 2x plus 1. So that's an increasing linear function. And if we could actually get to 0, it would have a value of 1. So it's an increasing linear function. It's going to go all the way up to here at 1. It's not allowed to get to 0, so it's got to be an open circle. But it's increasing linear, so that's supposed to be a straight line. Whoa! The more I try it, the curvier it gets. So that should be a straight line. Then the next one says, as we go between 0 and 1, so on our next interval, we have a value that's equal to 2. And on the left side, we're allowed to be equal to that. But on the right side, we're not. So we have to put an open circle there. And then on our last interval, from positive 1 onward, we're allowed to have 5x minus 3. So another increasing linear function, a little steeper slope. And if we were allowed to have a value at 1, it would be equal to 5 minus 3, which is 2. So this one is a linear function that goes up that way. So that's a very rough sketch of this graph, but it should be enough to tell us a couple of things about the limits. So the limit as x approaches 0 here, well, we're going to have trouble because coming from the left and the right on this graph, from the left and the right, we end up in different places. And it doesn't even matter what they are. We don't need to know those. We just want to find out overall what it is, and we can say that the limit does not exist. Alrighty. And for the last one, the limit as x approaches 1, well, coming from the left for that function, so coming this way, we're headed toward a y-coordinate of 2. And if we approach from the right on that graph, so coming from this side down here, we're going to get a y-coordinate of positive 2. So the limit as x approaches 1 of f of x here is actually going to be equal to 2. Okay? So we flip the page and we're at the your turn question. So if you want to pause the recording now and take a chance to go through and work through that stuff, have fun. And I'm just going to flip now to the solution. So you can have a look at the solution for that your turn question, and hopefully you get it correct. And if not, hopefully the solution helps you figure out why and how you can fix what you've done. And now we're just going to jump to the summary of key ideas for this particular section. And the summary of our key ideas here says, graphically, we can evaluate one-sided limits by following the curve toward x from both the left and the right, and that gives us both of those limits. And if we have different limits, it doesn't exist. But if they have the same limit, then the limit does exist, and it's equal to whatever that limit was, L. Okay? So that's a quick rundown on that, but we have to have agreement from the left and right for the limit to exist. And remember that it has absolutely nothing to do with the value of the function as long as we approach the correct places. So if the above condition is not met, of course, we say that that limit does not exist. Okay? So I hope all that was helpful, and happy studying, and good luck on your exams.